करके वो
Even people don't understand the importance of the
yes,
situation.
yes, yes. Even here only 50% people wear the mask,
Yeah.
and social distancing there sometimes maintained, sometimes not possible. Yeah,
Yes.
here in our small town, Chikkodi is a small town in Karnataka state, in Balgam district.
Mm-hmm.
So 2 3 days back, one of our departments, commerce, had gone to bus stand and the nearby vegetable area. They created awareness actually regarding mask wearing, and you should
Mm-hmm.
not spit in the public, like that.
Rana
Hello,
size.
Rana. Hello.
Hello, good
Good
morning
morning.
or good
Yeah, I'm
afternoon.
Uday Singh Rajput, principal of this college.
Sorry for the delay.
Yeah, no problem, no problem. Still time is there. Still 5 minutes. So the background of mine is, these are our founders of KLA Society.
Okay.
Okay.
I think you have heard of them. KLA Society, you have heard.
Mm-hmm.
And these are 7 Saptarshis, we call 7 Rishis, saints.
Uh,
And we have around 265 institutes in our society,
Wow, that's good.
starting from kindergarten to even medical colleges, universities.
uh, Hello.
Sidling, Dr. Sidling.
Sorry, sir. Actually,
Rana
Swastika
Sahaya
Banerjee ma'am having some internet issues, so she is not joining. So I'm just waiting for her. So I will just get you back to me, sir.
Okay, let me talk to her.
You just talk, Rana. Rana, sorry, I couldn't.
It's okay, no
see
problem.
you,
I
yeah.
just maybe I can just call.
You just check with her.
I think she will have internet issues. I am sure. I'm sure.
Rana, Swastika ma'am has joined, so no issues now.
Yeah, Swastika is there.
ಸರ್ ಯಾರಿಗೂ ಎಕ್ಸಿಟ್ ಆಗ್ಬಿಡ್ತಾರೆ ಒಂದ್ಸಲ ಹೇಳ್ಬಿಟ್ರಿ
Hello. Swastika joined?
Yeah, I'm here.
Yeah, welcome, Swastika. I am principal here of BK College Chikkodi.
Thank you so much.
Sir, principal sir.
Yes.
Speakers, please don't disjoin the meeting. Actually, don't disconnect your meeting ID. So, because we have continuous sessions, so first speaker will speak about 30 minutes, and then 10 more minutes for question and answers with discussion with the participants. And another speaker will take that. It will be continuous program. So if you disconnect, and again it will be a problem to rejoin. So please don't disconnect. And now I will start the program. So sir, can you go ahead? And I'm requesting all the participants, please unmute your video audios, and if possible video also. And participants, you can text your questions in chat box, those who are in Zoom meeting. And YouTube also, you can comment, there is a comment box, so you can comment your questions, and we will reach the speakers your questions, and we'll get back the answers after the speaker's speech. Okay, a very Good afternoon, all of you. Heartily welcome to International Virtual Conference in Advanced Materials for 2020. So this program is organized by Department of Physics, KLE Societies, Basavaprabhu Kore Arts, Science and Commerce College, Chikodi, Karnataka, India. I request Professor UR Rajput, our dynamic principal, sir, to welcome the gathering once again. Principal, sir, please.
Good afternoon, everybody in India, and good morning to all resource persons. It gives me immense pleasure to welcome you all to our prestigious KLE Society's Basavaprabhu Kore College, Chikodi. The physics department of our college has organized International Virtual Conference on Advanced Materials, for which I welcome heartily all the resource persons. The resource persons are Dr. Satyanarayan Goin, postdoctoral fellow with Professor Claudia Falser, Department of Solid State Chemistry, Max Planck Institute for Chemical Physics of Solids, Dresden, Germany. Welcome you, sir.
Thank you. Thank you very much.
I also welcome the second resource person, Dr. Anna Saha, postdoctoral fellow, Max Planck Institute of Microstructure Physics, Weinberg, Saale, Germany. I welcome you, sir. I also welcome Dr. Swastika Banerjee, postdoctoral fellow, Nano Engineering Department, University of California, San Diego, USA. I welcome you, madam.
Thank you so much. Yeah, it's my privilege to be here. Thank you.
Happy to see you all. I also welcome all registered delegates. Once again, I welcome all you. Thank you very much.
Thank you very much, sir, for welcoming the gathering. And now I request it's a time to make our day's keynote speakers. All the keynote speakers are very much familiar in their field. So myself, I'm going to introduce them. First, I would like to give a brief introduction of Dr. Satyanarayana Goin. So Dr. Satyanarayana Goin, before this, I would like to mention all three speakers are a very good friend of mine. And Dr. Satyanarayana Goin received his PhD degree in 2017. He received his PhD degree in 2017 from New Chemistry Unit, Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. Currently, Satyanarayana Goin is working as a postdoctoral fellow with Professor Claudia Falser. She is a very famous scientist in the world, so everyone knows her. And Claudia Falser in Department of Solid State Chemistry, Max Planck Institute for Chemical Physics of Solids. Dr. Satyanarayana Goin also received a very prestigious award. So that is Alexander von Humboldt, so Foundation of Germany. So I'm very much proud for that. One of my friends has received that award for doing postdoctoral fellow. Also, he has received several awards. With this, I welcome Dr. Satyanarayana Goin. So welcome for this conference.
Thank you. Thank you very much.
So second speaker, thank you. So second speaker, Rana Saha. So Rana Saha has received his PhD degree from Jawaharlal Nehru Center for Advanced Scientific Research in the year of 2017. And he is the student of Professor C.N.R. Rao and Professor A. Sundaresan. So presently he is a postdoctoral fellow with a famous scientist, that's Stuart Perkin. So he is a very good scientist. So, and also thank you, welcome you, Rana Saha, for this international conference.
Thank you very much for this invitation. And
yes. So now I would like to welcome Swastika Banerjee. So Swastika Banerjee received PhD from Theoretical Science Unit, Jawaharlal Nehru Center for Advanced Scientific Research. So now presently Swastika Banerjee is doing postdoctoral at University of California, San Diego, USA. So all the speakers have very much good knowledge on this on their field. So I request all the participants, please feel free to interact with them and gain your knowledge. So with this brief introduction, so I welcome all of you. Thank you.
Thank you very much.
So now the session is open to Satyanarayana. So you please continue the session.
Okay.
Satya.
So I'll share my screen now then.
Yes, of course, you can share.
Can you see my screen?
We are seeing only your face, but your screen has not yet shared.
Can you see now? Or
No, not yet.
I think the screen needs to be shared from the organizer side. They has to create some button or something.
there is no such option, right? I
They
cannot
should,
see.
I mean, the host needs to allow you to share their screen.
But I see the option share screen. I
Share
think
screen is there, Satya, in the
But I
bottom.
cannot see actually in
uh,
my case.
it's in the bottom panel after the chat box. After the chat,
Yeah,
uh,
share screen. One participant can share at a time, and multiple participant can share simultaneously. Which one to select? I don't know.
One participant maybe.
Satya, you share screen simultaneously start the PPT also. You will it will come, I guess, because I'm only your it's a
Yeah, I
online
think
Can you see now?
no, it's not yet.
But this is Rana. Can you try once from your side that you can share or not? Yeah, it is happening.
Yes.
Yeah, Rana's screen has
Yes.
shared.
Which option you selected? That multiple participant. I cannot hear you. I cannot hear you. Your microphone is on.
single. Multiple. Sorry, you have to share multiple. Check multiple. Does it work?
No.
Just try single, multiple, and then when you try, there are many other window will come and you have to select only yours.
Oh. Ah, okay.
Can you?
Can
Yeah.
you see? No?
Yeah.
I think it's okay, good.
It's coming.
Sorry. Now it's okay.
Yes, Satya. Yeah, now your screen has been shared.
Okay, so thank you very much for inviting me in this nice meeting, and I'm really happy to be here. So today I'll present some of the work related to thermoelectric effect. So, so there are some, I think, person want to join in this meeting. So I have to admit, or you guys can do it.
I admitted it. You can carry on.
Okay, so today I'll present some of the work related to the metal chalcogenides and topological materials related to thermoelectric energy conversion. So what actually currently we are doing in the Max Planck Institute, basically we are synthesizing different kinds of topological materials, and then we study different electrical and thermal transport properties related like anomalous Hall effect, Magnus resistance, Seebeck effect, Nernst effect, and thermal conductivity. So mostly I am focusing on the area of thermal transport, and our goal is to understand the role of topology in the thermoelectric effect and to use the topological material for the thermoelectric energy conversion. So this is the latest research interest in my research interest, specifically in our group in the Max Planck Institute. So today what I'll do, today I will present some of the in the area like mostly first discuss about the thermoelectric effect and how it can be useful for the energy conversion in our future energy management. And then I'll try to give some examples related to Seebeck effect, which is well studied in the direction of the thermoelectrics. And specifically in the latest direction, I'll discuss about the Nernst effect and one examples related to topological materials, how it can be utilized in the energy conversion application. So this area actually interesting, and this is a particularly new area. But before going to this particular example, I'll give some introduction related to thermoelectrics and Seebeck effect. So now let's move into what is a thermoelectric effect. So the thermoelectric effect is a direct conversion of the temperature difference in the electrical voltage, or vice versa. So generally you can use it for the power generation application in the Seebeck effect geometry, where you can give a temperature difference and you can generate a electrical current in the circuit. And in the second case, you can use for the refrigeration application, where you can give a electrical voltage and you can make a temperature difference. So you can use for the active cooling applications, basically in the Peltier effect geometry. Okay, so now why it is important to do thermoelectric research. So here I have shown some pie chart from the world as well as Indian prospect as well. So basically you see that the most of the inner form of energy that we are used are come from like coal or hydro nuclear power, and some like in the petroleum and the gas. So most of this we use for the electricity or in the transportation or commercial uses. And after the use of all this form of energy, around the 60% is rejected as a heat. So from this 60%, the question is, can we convert some of this waste heat into some useful energy? And that is the primary motivation to do the thermoelectric research. So from this 60%, if we can convert around 10 to 20% in some useful energy, then it can make a very significant impact in our future energy management in India as well as in the world scenario. Okay, so now where we can apply the thermoelectrics. So thermoelectrics has a lot of potential, lot of position we can apply this thermoelectric device, and you can convert the waste heat into the electricity. Like you can use for in the power plant in the big scale, and in the small scale, like in the automobile sector, we can use the thermoelectric device in the car exhaust pipe, and from there we can make the car hybrid in nature. And in the in the small scale, like in the cooling applications, they use for like microprocessor, the commercial cooler or warmer refrigerator. And even in the spacecraft also, this technology used for the long time, like NASA used this technology for their deep space probe missions, where they use the radioactive thermoelectric generator for the powering of the spacecraft. So in the deep space, you cannot utilize any solar power energy. So that is why thermoelectric is a very reliable source for the powering of the spacecraft. So they have used this technology for the Voyager missions, and till it is working. Okay, so now how to know a good thermoelectric material? So the question is, after now I have discussed the applications of the thermoelectrics and of the basics, and now how to understand a material is a good thermoelectric or not. So for that, this is related to the thermoelectric efficiency of a material, which is a well-known, we know from the textbook, that is related to Carnot efficiency followed by the thermoelectric figure of merit. So it's related to thermoelectric figure of merit, which is called ZT of the material. So generally, so if you know that the GT of the material, we can make a estimation how the efficient of the of a thermoelectric material could be. So if you have a ZT value, for example, close to 1, that means it's like efficiency is around 8 to 10%. So commercially, we have in the market now 8 to 10% efficient thermoelectric materials. Okay, now how to tune the ZT of a material, as the ZT is a very important parameter to get a good thermoelectric material. So the GT of a thermoelectric material is related to 3 interdependent materials property, like Seebeck coefficient of a material, electrical conductivity, and thermal conductivity of a material. So to tune the thermoelectric property, it is important to get control over all these 3 thermal properties of a material. So now let's see how to know a good thermoelectric material. Okay, so as I told, you need to have a good control over Seebeck coefficient, electrical conductivity, and thermal conductivity of a material. So that is why we need to have, you need to choose a material which have a low thermal conductivity. That means we know that generally glass-like material have a very low thermal conductivity. So glass-like property is important in a material. At the same time, electrical conductivity should be high. So that is possible to achieve in a metallic-like system. So metal we generally we know that have a very high electrical conductivity, and at the same time we need to have very high Seebeck coefficient. So that is possible to achieve in a semiconductor-like system. So in literature, people have seen that all these three properties generally get optimized in a material in a 10 to the power 19 to 10 to the power 20 carrier concentration regime. So where you can generally achieve a maximized ZT value of a system. And that actually a very challenging task. Get all three material property in a single material. So that is why the designing of a good thermoelectric material is a very challenging area. Okay, so there are some concepts known to tune the property of a material. So these are different concepts known in the field which used to improve the overall thermoelectric property of a materials, which I'm not going into details, but if you are interested, you can go through this review article where all this has been very nicely discussed. And from the summary, I can say that the best thermoelectric material could be the heavily doped narrow bandgap semiconductor materials. These are generally the good thermoelectric material known in the literature. Okay, so now come to the device, how the thermoelectric device looks. So now, up to now, we know the material. Now, this is how a thermoelectric device looks like. So thermoelectric device where you have like a P-type and N-type material in the series, and you can connect this in many legs in series, and you can construct a thermoelectric device, and you can give a temperature difference, and from there you can use for the power generation applications or in the refrigeration application, depends on the maximum value of GT where it can be achieved, or which temperature you get the maximum value of ZT. Okay, so this is a video. You can see a prototype how the thermoelectric technology works. So you see here, there is a cold water container, and there is you'll put a hot water here, and from there you can generate a temperature difference, and from there you can run this fan. So this is a prototype how the thermoelectric works. See, this is down now. The fan is rotating. Okay, so this is just to give you an idea how this works. Okay, now how to make a good thermoelectric material in the lab. So how we generally do different synthesis of thermoelectric material. So different material can be synthesized in a polycrystals form, like we can use the high vacuum seal reactions where you can seal the material in the quartz tube, and from there you can get an ingot, and from you can cut into bar and coin shape for the thermoelectric measurements. Also, you can do different kinds of single crystalline material synthesis as well. Like you can do like chemical vapor transport synthesis, where you use a polycrystalline powder to grow the single crystals by using a temperature gradient in the furnace. And the flax method, this is also, you can use a molten flax for growth of the high quality single crystals. And the Bridgman method, where this method generally used for the growth of very high quality large single crystals. So this, and after the growing polycrystals and single crystals of the material, you can do different characterizations like powder X-ray, Laue diffraction, ACM, EDAX, ICP, TEM for the characterization of the polycrystals and single crystals materials. So after the synthesis, then we go for the measurements. We do a lot of, we can do measurement like in the high temperature, this equipment generally used. And for the thermal conductivity, we can use the like LFA, NECH. And for the low temperature, so if you want to know the refrigeration property of the thermoelectric material, you can do the low temperature transport as well in the physical property measurement systems. And generally, standard samples required for the thermoelectric measurements. This is the dimension for generally used for the thermoelectric measurement. Okay, so now this is to give an idea how generally we can estimate the thermoelectric figure made from the different measurements. So you can measure the electrical conductivity. This is a typical schematic representation how the curve looks for the electrical conductivity. And this is how the Seebeck coefficient curve look after measurement, and this is the thermal conductivity. So you generally measure the electrical conductivity, Seebeck coefficient, and thermal conductivity, and from there we can estimate the overall thermoelectric figure of merit, and this how it can looks the overall curve, the thermoelectric figure of merit from all the physical properties measured data. So this is state-of-art thermoelectric in the literature. So you can see there are a lot of materials has been developed till now in the literature, like N-type and P-type material regime. So N-type means the whole electron is the major charge carrier in the system, and P-type means the whole is the major charge carrier in the system. So both an N-type and P-type material are essential for the construction of a device, and that is why both direction has been taken care. And you see there is a clear sudden jump in the thermoelectric research after the 2000 year 2000 is because a lot of different concept has been developed, and also the energy crisis also pushed this field, and now there are a lot of activities is going on in this direction to grow different to develop different thermoelectric materials. So the most of the cases, as I have mentioned earlier, the heavily doped narrow bandgap semiconductors are generally good material for the thermoelectric research or thermoelectric material. Okay, so now let's move to two examples that I'll try to give you in this direction, like in thermoelectric energy conversion, one in the metal chalcogenides in the Seebeck direction, and then I'll discuss about the Nernst effect, which is a little advanced and which is going on recently, is a lot of attention, especially for the topological materials. Okay, so now this is actually I started during my PhD. This is a 1562 class of semiconductor metal chalcogenides. So this material is known to show crystallize in a NaCl structure, which is a standard rock salt structure. So if you compare the structure with the PBT, which is a champion material considered for the field of thermoelectrics, in the PBT side you have silver and antimony disorder, and in the lead side, tellurium side, you have the selenium. So it has a disorder cation sublattice in the system. Okay, so now why this system is so important, why you choose to work in this system. So as I told you that you need to have very low thermal conductivity to get a good thermoelectric effect. So that is why we chose this system, because this has a very different bonding type and electronic configuration in the system, which helps to get a intrinsically low thermal conductivity, or which helps to get a low phonon thermal conductivity, which leads to low thermal conductivity on the system. Like it has a lone pair of electrons in the like antimony, like so s2 electrons, which results in very huge lone pair electron clouds, which deform the bond arrangement and decrease the thermal conductivity of the system. And additionally, it has a disorder cation sublattice, which results in low thermal conductivity. And another important point is it has a very favorable electronic structure. It has a multiple flat bands in the system, which results in high effective mass, carrier effective mass, which is important to get a high Seebeck coefficient from the Mott equations you can see from here. Now we know that it has a good Seebeck coefficient, good low thermal conductivity. And another important parameter, as I told, you need to have good electrical conductivity. So for that, we try to carrier engineering this system by doping of the system by the P-type dopant. Okay, so this is the idea to start this work. So here is the synthesis strategy we have used for the pristine as well as for the doping. We use the lead and bismuth and we can get a very nice ingot for the transport measurements. And then we cut it into bar and pellet shape for the further study. And this is some of the characterizations. So as I told, you can characterize by powder X-ray. You see the very nice single phase nature of the samples. And from the transmission electron microscopy also, it shows a very homogeneous nature of the samples. So from there, we started further measurements. And from you can see that this has a very low thermal conductivity. It's basically a ultra low thermal conducting system, which has a very low thermal conductivity compared to, if you compare with the champion like PBT or nanostructure PBT system as well, it's a very low thermal conductivity. So this is because of the high anormality of the bonding, and you have a very special atomic arrangement like disorder atomic arrangement in the system, which results very low thermal conductivity of the material. So furthermore, we studied the electrical conductivity and the Seebeck measurements, and which shows very high improvement in the electrical conductivity after doping with lead and bismuth in the systems. And as a result of improved electrical and thermal transport, we have achieved a improvement of the thermoelectric figure of merit approximately 190% in this metal selenide system, which is actually a record in that time. So we further calculate the thermoelectric efficiency from the single leg, and we found this system actually shows a efficiency approximately 9%, which is efficiently and is a market-based, matches with the market-based metal telluride system. So this work actually one of the first examples in this area of ultra-low thermal conductivity, which is now gaining very much attention in the area of thermoelectrics, which shows the ultra-low thermal conducting metal could be a potential candidate to achieve a high thermoelectric figure of merit in the system. And if you now look in the literature nowadays, every day you can see some paper which discuss about the importance of ultra-low thermal conductivity in the area of thermoelectrics. So this is up to this much I discussed some of the conventional work which people do in the thermoelectric research, like in the Seebeck effect direction. And now this is a new area of research which is now in the couple of years it's opening up in this direction, which is enhanced Eddington effect, which is basically a thermomagnetic effect. So in this effect we generally use a magnetic field in the orthogonal direction of a temperature gradient, and you can get a electrical voltage in the perpendicular direction, and from there you calculate the Nernst thermopower of a system. So this is an idea in the there is some raised hand. I think I can take now, or I can.
Thank you very much, Satya, for an exciting talk.
Yeah.
So you have given very detailed information about the thermoelectrics part, and few questions are there. So you please answer them. The first one is metals or semiconductors. So which one is the best for a high ZT, and how it will give high ZT?
So basically, semiconductors are good. So as I told here in the introduction slides, you can see. So generally, you need to have a carrier concentration regime 10 to the power 19 to 20. So generally, it's a semiconductor, heavily doped semiconductor regime, where generally you can get a good thermoelectric property. So I can say the semiconductors are good for thermoelectric effect.
Yeah. Okay. And second question, what exact strategy we have to follow to choose the materials for getting high ZT?
So strategy, as I told, you need to have good electrical conductivity like metal, high Seebeck coefficient like semiconductor, and low thermal conductivity of the glass. So this is actually a very challenging task. So you have to optimize all these three properties. So that's why I told you first you have to choose a semiconductor system. Basically, it should be a narrow bandgap semiconductor, and then you have to see how the carrier concentration in this system. If the carrier concentration is low, you have to dope the system to improve the carrier concentration so that you can get a decent amount of electrical conductivity of the system without losing the Seebeck coefficient. And then you have to get a reasonably low thermal conductivity. So this is actually another challenge. This is because if you increase the electrical conductivity, at the same time you can improve the electrical thermal conductivity of the system, because the electron also, or the charge carrier also can carry the heat in the system. That is why it is you have to take care of all the part. So it should not be very low electrical conductivity. At the same time, you should not be very high thermal conductivity. So that's actually a challenge, and you have to play with that. There is
so basically we have another two questions. Yeah. You please go ahead. You are explaining something.
Okay, so I can go now.
Yeah. What is the lowest thermal conductivity we can achieve?
So thermal conductivity, basically, I can say that So if you have a system, generally, see, in principle, it can be 0, but it is not possible to achieve. Okay, so you have always a lattice thermal conductivity which is contributing from the phonons. So I can say till now in the literature, people have seen like 0.3, 0.4, you can get it.
Okay. Yeah, one last question. How you will measure the seepback coefficient for very small single crystals?
For small single crystal, you need to have special setup. I have not shown here, but specially designed setup is available. We can do here, but in the commercial machine, you cannot do it. In commercial, like in the GM3, people generally use.
GM3 it's not possible. Yes.
It is not possible, but in the thermoelectrics, we have some special design or customized setup. It is possible. People can do in the 1 millimeter sample also. It is possible to do. So for that, generally we do in the low temperature in the PPMS system, but in the commercial high temperature setup, there is no such. Till now, I don't know any setup can do in the high temperature. Yeah.
Okay. So now there are no questions. So really, it's an exciting talk, and there's huge responses from the audience. So I thank you once again from my side, and yeah. So thank you very much once again. So I will get back you again. And now I request Rana Shah to please take the session.
Thank you very much. You can hear me?
Yeah, I can hear you. You can share the screen.
Yep.
Yeah.
So can you see my screen? Am I audible? Hello? Can you see the screen?
Yes,
I can see. Yeah.
Okay.
Yes,
okay.
it is shared now.
Okay. Oh, first of all, I would like to thank Sidaling for this kind introduction, and as well as the invitation to present this work, which I have been doing for last 3 years in Max Planck Institute in Halle. So it's always nice to get back to people of Karnataka, because I started my scientific journey from Bangalore, JNCSR. So let me first welcome you all, whoever here from Germany. So it's I live in somewhere in the east of Germany. If you start from Bangalore, so it's Berlin here, and from Berlin to like 160 kilometers away, this small city called Halle. Zale is the river, and we have our institute in this city. So this is our institute. It's relatively new department, I would say. Our department is very young. It's because our professor was here in just 4 years ago from IBM, and now we have established a very world-class facility in our department. So we have a lot of our focus of the main work is here Spintronics material and devices in our group. So first, I would like to, before I start my talk, I would like to first thank my professor Stuart Parkin for giving these exciting facilities and research opportunity in this group. And this is our team, which I'm working with. And also, of course, I should thank Professor Claudia Felcher for collaboration, active collaboration with their group for the samples. So as we know today, we are full of digital data. And this digitalization actually it was possible for last few decades because of miniaturization of the size of the chip. And because of that, now we can do a lot of computation, and we can store data in a very smaller space. As you know, yesterday there was an announcement from Sundar Pichai, CEO of Google, that he's going to invest $10 billion to India in the next coming years for the Google for India digitalization. So you can understand the digital world is going to increase dramatically. But one has to remember, when this digital data, as today's world is full of digital data, when you're going the digital data, so at the same time, the device which we are using, the size is decreasing, because the Moore's law predicts that the transistor size will decrease in every 2 years, the integrated circuit. But when you decrease the size of the circuit, what happens? The problem happens because you induce a lot of heat in the material. So today's digital world was possible because, as we know, like we can have a lot of data. We can have like in a pen drive or whatever, we can take data and we can upload in the cloud and we can access from anywhere in the world. But how this data gets stored? This data basically gets stored in a hard disk, huge hard disk, which is on your left side is a big data center of like Google or the Facebook. So this it was possible to store all this data in hard disks. So if you look at the hard disk here, I can show you here. So this hard disk is from 1960s or from the IBM first hard disk. Is like, you can see it's like 24-inch diameter of each disk, and it could store only 28 megabyte data in a size of a refrigerator. And the today's hard disk which you have on the right side is like 2.5 inch. So you can understand that there's a dramatic progress of data technology which was possible today because of the miniaturization of the devices. So how is this possible? As we all know, the hard disk looks something like that. And this hard disk has a needle, which is a read head or write head here at the tip of the actuator arm. And this is a platter where basically this needle can move backward and forward. So what it actually does, it is actually the needle tip has an electromagnet which can actually write a magnetic regions of up and down spin as black, blue and the red, and that's how you can write data. And then you can read data with the help of a write device also installed at the tip of the head. So this was possible because of because of these properties of electrons. Electrons has a property called charge, as well as it has a property called spin. So because of the spin of the electron, it is possible, spin is quantized because it's a quantum mechanical phenomena of electron. So it has either minus up or the plus up is the charge of the electron. So you can have either up or down. So you can store data basically as up or down in a hard disk at the form of a 1 or 0. So for example, if you have a 1 or you might have 0. So the data in the computer hard disk, as I showed before, it was actually stored in the form of a 1 and 0. But now we have to go back how it was possible, because if you let us take a simple metal, copper metal, as we know you use in the household everyday wear, this copper metal which has equal number of up and down electron at the Fermi level. But in case of magnetic metal, what happens? You have an unequal number of up and down electron at the Fermi level. So what happens when you pass a current through a magnetic metal using a battery? For example, in this metal, if you read one, if you pass a current which has equal number of up and down electron, and now when the current passes through this electron will align to the magnetization of the ferromagnet. So if you have an up and down electron coming to this metal which has only up spin, so finally you will collect a spin polarized electron. Basically you will have only up electron and the down electron will be scattered. This phenomena has tremendous application. So what happens actually? Now if you can make multi-layer made of a magnetic metal, another magnetic metal separated by a non-magnetic chromium metal. Remember, these are very thin metal, and if these magnetic metals are separated by a antiferromagnetic chromium metal and the separation distance is like less than the scattering length of the electron. So what happens there is, when you measure a resistance, what happens when these two layers are anti-parallelly coupled, high resistance, but when you reduce the when you increase the magnetic field, there the magnetic spins are aligned. So depending on the orientation of the spins, there is a huge change in resistance, and this is called giant magno resistance phenomena. and for which was discovered by these two gentlemen, Professor Albert Fart and Professor Peter Grunburg, and they were awarded Nobel Prize in Physics in 2007. And this phenomena has dramatic effect on the data storage. So because of this effect, today's GMR head, this JMR, giant magnetic resistance head, is used to read a small magnetic field generated out of these magnetic beats, as I showed you in this previous schematic of the hard disk. So this created a new field of science and technology. Of their discovery is called spintronics, the spin-based transport phenomena. So the immediate application is today's world. We see because of the spintronics, we can store data in a small space, a huge number of data. As you can see, today we can store even in a hard disk is like 4 terabyte data, which was not possible even 30 years ago. So another phenomena of this spintronics is that now in the previous I mentioned that if you have two magnetic layers separated by a non-magnetic metal, you have a huge change in magnetic resistance. It is another memory was also possible is like if you have a two metallic layer separated by a very thin insulating barrier layer. So as we know, insulators actually doesn't allow you to go through the electron pass through. But if the insulating layer here is shown as the MgO, if it is thin enough, it can happen. Electron can basically tunnel. It's a quantum mechanical tunnel. Electron can tunnel from one layer to the another layer. And this tunneling process again depends on the state of magnetization of these two layers. For example, if you see here, if these two layers are red colored, if you think both are ferromagnetic layer, so electron can tunnel easily from one state to other state because of same spin polarization, because both are up spin, let us assume. As you can see here, it can easily tunnel from up to up. But if the magnetization of this layer is down, so this probability of tunneling of the electron through this thin barrier dielectric, it reduces. And because of depending on the orientation of the magnetization, this tunneling happens. So you can have a two state called 0 and 1. So this can act as itself as a memory cell unit. So what is actually done? So you can use such small this structure in between a cross array in the form of, you might have of MRAM, is a magnet resistive random access memory. So basically this is a solid state memory, unlike in hard drive where the needle needs to move, which is a mechanical, but it is much more reliable compared to hard disk memory. Now what happens here, if you put these small units in between to this cross array, so you can pass a current through this word line and the current can exit through this bit line, and you can read by passing current whether these states are parallel or anti-parallel. When they are a parallel state, you have a 0 state because of there is a flow of current, and when there is an anti-parallel state, there's a high resistance state, no current can flow, and there'll be a state 1. So in this way, one can read this each of the magnetic using this magnetic tunnel junction. Now the question is how this you can write. Also, you can write this. How you can write? You can pass a current, higher current. What it can does? Suppose you are passing a higher current. This is the structure. If you assume, if you pass a high current, what happens? As I mentioned, when it goes through a ferromagnetic layer, the spins become polarized because means incoming electron will follow the magnetization of this layer. So the up spin, and then we enter into this ferromagnetic layer. This ferromagnetic layer is the left side. This ferromagnetic layer is fixed ferromagnet, like the magnetic relation cannot switch. On your right side, this layer can flip the direction. So what happens when this spin crosses the first layer? So it takes the up spin because it is a fixed, and when they enter this layer, this spin transfers its angular momentum to this spin on the right side, and because of that it feels a torque, and by this way the electron spin can switch. So it can switch from parallel to anti-parallel or anti-parallel to parallel. So that's how you passing current, you can write 0 and 1 bit by passing current. Also here you can read by small current, if you pass you can read whether it is 0 and 1 state. So So in this way, you can have a solid state memory. But this has also some limitation, because in practical scaling, sometimes scaling it's a issue. So we need, but this memory is quite expensive as compared to the hard disk, which is quite cheaper. But hard disk is much more unreliable in a sense, because you can lose your data, because the pin which moves back and forth, it can crash. You might have encountered this phenomenon of hard disk crash. But hard disk can store a lot of data in a very small space. But now, so there is another the data technology which was proposed from IBM, from Stuart Parkin, where you can have a nanoware, which is a three-dimensional nanoware. This nanoware, you can have some magnetic domain wall. What is magnetic domain wall? If you have a spin up and spin down, in between these two transition region is the domain wall. So what you can do, you can pass a pulse current and you can move this domain wall from left to right or right to left. And in this, you can read at the bottom here with a reading device or the writing device, something like that. So as I mentioned in the previous case, TMR, tunneling magnetic tunnel junction, can be used as a reading device. So what you can do, you can install a TMR device here to read each of these red and black colored, these are magnetic domains. So each of these domains store data as 1 or 0. So up domain 1, down domain 0. So here basically you can read. So what is the advantage of this new concept is that in the hard disk, where you can, it was a planar storage where you can store data here like 1 bit, but by passing these hundreds of domains through this in the same place, now you can store 100 times data. So basically, you basically can store in the same place 100 times more data. Moreover, in this case, during this movement, there is no mechanical part, unlike hard disk needle. So there is no probability of crash, and it can actually run at a very low energy cost. You can have billions of these race tracks on a silicon chip, as you can show here, and you can have exceptional capacity and performance. So how does it actually, you can actually move this using a current. So I can just show you a schematic here. So for example, if you pass a current, what happens? Something called the current, the spins are like, spin directions are like separated out, called spin Hall effect. So this spin applies a torque on the upper spin. Upper spins are these, and then it can rotate. So using, this is called spin. This is a magnetic metal, which is top of a heavy metal, and in the interface you have a spin polarized current, and this spin polarized current actually applies some torque, and because of that, the domain walls which you see in your left side, it's actually moving from left to right or right to left. In this how actually you can move this domain wall back and forth, and you can move your data. So one of the just example of this is a 3D version. So, and this is our like one of the example prototype of two-dimensional domain wall, a two-dimensional device. You can see this is the rest track, and you can pass current through this device. So if I compare today's various memory technologies, so today we have a NAND flash with a flash memory, which is a very like a 3D kind of integration, high density, and also like you have like a hard disk drive which are high write endurance. You can write many cycles and read it many cycles, but at the same time, if you want to have a small latency, like if you have writing erasing time, it is comparable to the like a static RAM or dynamic RAM. So race track memory, which I proposed at the last memory concept, which actually combines all of these best in one memory. So it can have a high density, it can have a high endurance like a hard disk drive, and it can have a faster read and write, and it consumes very low energy. So race track memory is a very, very reliable. Future memory is going to come, and it will have a at least 10 years lifetime. So this race track memory can also, as I showed one-dimensional spin, I showed a domain wall, you can also use some kind of non-collinear spin structures. So non-collinear spin structure, you know, these are parallel spins, ferromagnet or anti-ferromagnet. And you can have also, because of frustration, some kind of non-collinearity. But we are interested of some kind of non-collinear structure, which is a chiral non-collinear structure. What do I mean by chiral? Like your left hand and right hand. If you have some kind of spin structure where you can non-superimposable mirror images, those are very potential kind of structure which will be useful for this racetrack application. So when you have some kind of magnetic interaction, which is a non-collinear, this is called Zielinski-Moria interaction. So you can have something like this kind of non-collinear structure. Spins are like going like a helical motion is going from counterclockwise or right-handed or left-handed fashion. So this this actually forms another special kind of structure when you can twist this structure too much. It's basically, you remember ferromagnet all are parallel. Some special kind of chiral interaction makes is twisting the structure. When they're twisting, they form some circular kind of structure like that here. These circular structures are called skyrmion. It's actually some kind of, it has a topological protection. What do you mean by topology? I mean the winding of the spin. And this you can calculate in this way, and this is basically quantized. So basically, because of this topological quantization, and these are very tiny size of nanometer size, it's like starting from 10 nanometer to like hundreds of nanometer. And these structures are very potential non-collinear chiral structure. What do you mean by chiral? Means they can, if you go from this along this radial direction, it can go counterclockwise or the clockwise direction. If you go along this direction, it is rotating either left-handed or right-handed. And another structure called anti-skyrmion, where you can have this kind of structure, alternating arrangements are there. There are many types of such structures, but I am interested on this kind of structure, which is some kind of chiral anti-skyrmion structure. So why these structures are important? As I mentioned in the racetrack case, you had these magnetic domain walls can move. So we can use this chiral structure instead of domain walls. You can see if we have this kind of structure, this is a simulation, they can move from left to right with the help of current. So because of this tiny nanoscopic size and because of the equal spacing, you can store more data in the small space. So this is one of the potential. So I will maybe briefly discuss of this structure. How is these structures is what is the properties of these structures? So I'll show how this structure you can make it, how you can stabilize them, how you can tune them, and what is the why they are interesting. So this is the first example of this structure which was discovered by a German group in Munich by neutron scattering. The six-fold, you can see the structure has a six-fold symmetry, which is indicates this is skyrmion phase here. This is skyrmion. So you start from the helical phase, as I told you, and then you apply magnetic field. It goes to some kind of, this is a skyrmion structure, and you further apply magnetic field, it goes to conical structure and it goes to ferromatic structure. So this you can also look directly using an electron microscope. So this electron microscope image looks something like that. You can see these vortices. These are chiral vortices of skyrmion. You can also look this structure using a magnetic force microscope, like a vortices you can clearly see. So these are from the bulk single crystal data. You can also stabilize them using in a thin film, using, for example, because real application you need actually a thin film in your device. So in the thin film, people have stabilized using scanning transmission, scanning tunneling microscope. You can see they can create it, they can delete it, and also people have shown using, see, this is the some domain wall which is outburst to magnetic bubble skyrmion here. And also you can have a multi-layer structure, A, B, like multi-layer of consists of, say, iridium, cobalt, platinum. You can create some kind of magnetic interaction at the interface of heavy metal and the magnetic metal. So you can have this kind of, these are the ways, so how you can have various ways you can create these skyrmions. There are many ways you can create skyrmions. So the idea is how you can use this skyrmion for storing data. So as I said that these fermions actually you can use a current, they can move, but how can you can read this? You know this Hall effect. So basically you pass a current in a magnetic material. So you have a Lorentz force and you can accumulate the charges, you can develop electric field, you can read the Hall voltage. Similarly, when the electron passes through a Skyrmion material, what happens? They gather some kind of inner magnetic field and it gives rise to some kind of Hall signal. That's how you can detect the skyrmion. But when the electron goes to the transverse direction, it also applies the opposite force. So skyrmion actually moves, and actually skyrmion, when you apply a force, skyrmion should move in a straight line, the racetrack as I mentioned, but instead of moving in a straight line, it moves sideways. When it moves sideways, what happens? Instead of going straight, you can hit the wall, you can lose data, because each skyrmion stores data either 1 or 0. So this you can understand with this famous soccer shot of Cristiano Ronaldo. So when he made in 1997, the ball, instead of going to the goal post in a straight line, you can see it went in a very curved way. So skyrmion is actually following the same thing. When you push a skyrmion, instead of going in a straight line, it goes in a curved way. And this is called because of some kind of force in physics, which is called Magnus force. But this is not good for real application, because if a Magnus force, you will hit your skyrmion with the boundary of your device and you will lose data, which is in a, you can see here, if you apply force, the skyrmion moves in your transverse direction. It never goes in a parallel direction. So this is on the disadvantage. To avoid this disadvantage, we use another structure called anti-skyrmion. So this is the structure of anti-skyrmion, where it is expected because of some anisotropic structure, it can move in a straight line. So we use this material. This is called tetragonal inverse Heusler material, which this material we get in collaboration with Professor Claudia Felser group. So this is a metallic material, and this material is a tetragonal symmetry it has, and it to stabilize this kind of material, you need to have a particular symmetry, which is called D2D crystallographic symmetry. In this symmetry, you can actually stabilize like some kind of anisotropy, and also you can have some kind of isolate, some chiral magnetic interaction. So you can see here, it is the spins here. We use this kind of interaction where the spins are aligned along the C axis of the tetragonal axis, where this manganese moment has two type of manganese. One is in the plane of the tin, another in the plane of rhodium, say heavy metal, and the spins are canted. So because of some special kind of magnetic arrangements, it actually holds a promise of holding some kind of this skyrmion structure, this non-collinear chiral string structure. Let's look at this. How we do look at it? Such a tiny structure. To look at this tiny structure, we use something called electron microscope. As you all heard of electron microscope. So what we do, you pass a high energy electron. Say, let us assume this is a magnet made of this Heusler material, is a schematic. You pass electron, and this electron actually gets deflected because of the Lorentz force of from this material, and they generate some kind of magnetic contrast. And because of this magnetic contrast, they will look like that. So you have a skyrmion of black skyrmion, which you have this kind of contrast. If you have a nail skyrmion, you will have no contrast. But when you have an anti-skyrmion, which is I'm interested in, which will have something like that, this contrast, you can see here, there is no contrast. And when the scattering, when this deflection happens, the contrast is generating something like that. So you have some kind of clover leaf like of structure where there's two bright and two dark spot. If you have this kind of contrast, by this way, we can have this kind of spin structure we can actually detect. So this is really interesting. So you can see this is the real image of anti-skyrmion, which obtained from the microscope. These are the one-dimensional helical structure. When you apply magnetic field, they form something like that. So each one of them will be a potential element for the data storage in future, and this one of them will store 1 bit. When their presence will have 1 bit, their absence 0 bit. So if you have if you can increase the density, for example, in this space, now if I have a, like, say 20, instead of 20, if it is 2000, you can imagine the data density in the same space increases at least 2 orders of magnitude. So this structure is also stabilized in the microscope using some special kind of arrangement. So you can see this is the structure, real structure, and this is the forms a lattice of this magnetic antiskyrmion, and when you apply magnetic field, they actually vanishes to the ferromagnetic state. Even in the ferromagnetic state, they're still survived because of their some special topological protection. And we can actually stabilize, we can study as a different function of thickness. We can see, you see at a different thickness, these are the three different thickness of the sample. We have a different degree of variation of the stability of these spin textures. And then actually we studied, these are the different magnetic antiskyrmions which have a different stability. And I will go a little fast, I am losing time. So they have a wide range of temperature and field stability. These are the phase diagram, means you need to know at what thickness you can stabilize this antiskyrmion, because when you make a device, you need to thin down or you need to change the thickness. So you need to tune the right thickness where you can have these magnetic antiskyrmions. And these antiskyrmions, and these are the skyrmion phase diagram. You can see in the case of skyrmion, this red region actually shrinks when you have higher thickness. But in the case of antiskyrmion, what happens? This thickness dependence stability is like independent, like they're more or less independent of the thickness because of the difference in the symmetry of these two material, hosting one on the left side hosting antiskyrmion, right side hosting skyrmion. So this skyrmion is also possible. You can tune the size of the skyrmion. As I mentioned, if you have a, if you can have like a, instead of 20 skyrmion, you have a 2000 skyrmion, you have more data density. So increase the density. So you have to have some kind of stability. So what we see here, like we can, by tuning the thickness of the material, we can have, you can see the thicker part, thinner part, you have a smaller size, and the thicker part, you have a larger antiskyrmion. In this way, you can tune. And also you can see this size of the skyrmion, and different, you can see from left side to the right side, the size of the skyrmion actually increases. So you can see this is the thickness. So if you want to make a device, so you must know that, okay, so I know at what thickness, how much skyrmion size, and how much is the density. So if I have a map of this, now you can make material, you can do this investigation. And also these are the antiskyrmion. So it is also possible by, in the same material, you can have a different type of, you can go from, for example, antiskyrmion to some kind of skyrmion material. So what happens? This is your, remember, this is the skyrmion, this is the antiskyrmion. But remember, these two chiral spin structure are very much symmetry dependent of the material. They cannot coexist in the same material. But what we have observed, that this is your antiskyrmion material. So what we have observed, by tuning some kind of magnetic interaction, by playing the thickness, we can transfer from antiskyrmion, this antiskyrmion, to skyrmion. But that skyrmion structure is not the same as this skyrmion. This is some kind of elliptical skyrmion. So in a material, you can have two type of chiral spin textures. So what is the implication of these two types of spin textures? So what happens actually, you have, you know, the magnetic data, temperature dependent magnetic data. So here you see the magnetization value is higher, here you have a lower magnetization. So when you have a higher magnetization data, you know there is something called magnetic dipole interaction. When you have a stronger dipole interaction, you can make antiskyrmion to be stabilized in the form of a skyrmion texture, which is here. But when you have a lower magnetization, you have a lower magnetic dipole interaction, so the antiskyrmion survives. So in this way, in the same material, you can have two different type of topological structures. So this is my final slide. So what you can do with this kind of skyrmion and the antiskyrmion. So let us see in a material, is a real image from transmission electron microscope. You have a skyrmion and you have an antiskyrmion. So now you can make a racetrack device where you can store data in this way. So antiskyrmion will store data, for example, 0, and skyrmion will 1. So in this way, if you make a strip of a nanowire where you have a 0 and 1, you can store data in this way. This is one of the possible way of storing data using both skyrmion and antiskyrmion in a racetrack device. Okay, so let's summarize my talk. So I showed you that we have observed antiskyrmion using transmission electron microscopic image. These are the real images of transmission electron microscope image, and we have seen this it is very important to know the stability. So in a thinner region, you have a more number of skyrmion. In a thicker region, you have a larger skyrmion and less density of the skyrmion. And you can actually tune the size of the skyrmion to have a higher density, and more data can be retained there. And also we have shown how it is possible to actually make anti-skyrmion and skyrmion one material, and you can actually have a racetrack out of this. So with this, I actually stop here. And if you have any question, any doubt, please write to me in these are my email ID, and feel free to ask me question. And thank you very much.
Thank you very much, Rana. It's really very interesting and a very advanced talk. So from the audience, there is a huge response. So we got almost around 8 to 10 questions.
Oh.
So I will read one question. So you please answer them. The first one is, any idea about the diamagnetization and how efficient is this process to tackle current energy storage?
Okay. So first of all, diamagnetic material in this sense is not useful, because diamagnets has a these are not magnetic, first thing. So it is not at all useful. And second question is the energy storage. So basically what we are doing, basically it's not basically energy storing here, unlike what maybe the next speaker will tell about this energy storing more on the things. So basically what we do today, for example, if you are using a hard disk, for example, and this hard disk, because of the mechanical movement, you need additional energy, right? To anything you move, any work you do, you need some energy. But if you make, for example, now today's electronic device, you can make that it can take less power from the external electric source, so you can save energy. So you have to make devices much compact way, so you can consume less energy. So in that way, it is not really, it is really consuming less energy. So in that way, you can say it's energy, less energy hunger. It has a less energy hungry. So in that way, I would say, but it's not really making energy or storing energy. It's basically consumes less energy. Okay.
Rana, second question. What is the long-term applications of skyrmions?
Yeah, because skyrmion is very new field. It's just 1 decade research. It's not much people are working in this field. It's just 10 years. So there is a high potential in this field actually, because the main reason why skyrmions are useful, because if you can see in this schematic, these skyrmions are actually having a very smooth structure, because this skyrmion actually, you can, when you move the skyrmion, they actually there is no movement of atom. So atom doesn't move in the lattice, atom remains same, only the spin actually is moving. So, and since they're very tiny in size, so, and they have a topological, some kind of topological protection, you cannot destroy them. It is the most, and they are very defect insensitive. In a material, when you go real material, there will be always defect. So because of that, what happens, you can move them at a lower current as compared to domain wall, which I like, as I showed in the beginning of my slide, where to move them, because sometimes they are pinned with the, they're pinned with the defect. So you move them, you need to push extra energy. That's how you consume more energy. But in the case of skyrmion, they consume very less energy, and so they can easily move so they can store data. So in that sense, skyrmion is very in my mind, is very potential candidate in the future data storage in the racetrack. Racetrack is a technology where you can, skyrmion is a information carrier. Yes, next.
Rana, next question.
Yeah.
What about future room temperature skyrmions?
Oh, already we have a room temperature. By the way, whatever I have shown you, these all are room temperature. So most important thing, this today's my talk, anti-skyrmion is called anti-skyrmion because it has some kind of, you can think of a skyrmion as some kind of charge is +1, not electrical charge. It's called topological charge +1. Anti-skyrmion is a charge of -1. So these all are room temperature observed, but people have already observed room temperature skyrmion even in the thin films.
And
the drawback,
next question, which type of materials are generally required for magnetic domain wall?
You need you need some kind of ferromagnetic material like cobalt, iron, nickel.
Okay. Next question. What are the factors affect the most in skyrmions?
Okay, so this is a very this answer is very long, but let me try to answer this. So that's affect me in terms of their stability, or in terms of what kind of, I don't understand the question maybe.
Okay, so you can we will get back the answer later. So next question, what is the Magnus force and how it comes?
Oh, okay. So Magnus force is like it comes from the skyrmion. Actually, what happens basically, this skyrmion itself, each of the skyrmion, they can have some kind of, when you pass an electron through a magnetic field, this electron will passing a magnetic field, they acquire some kind of phase called Aharonov-Bohm phase in a physics term. This Aharonov-Bohm phase. So what happens when the electron actually passes, electron means when you pass a current, the electron passes, a spin polarized electron passes through a skyrmion. The skyrmion itself is a source of tiny magnetic field, even though there is no real magnetic field. Skyrmion itself provides some magnetic field, and because of this magnetic field, this electron actually gains some kind of phase in physics term called Berry phase, and because of that, what happens basically, this coming electron is feels some force, and it feels some Lorentz force, and it diverts in the transverse direction. To counter that one, the skyrmion also feel some force in the reverse, that is called a Magnus force, which is that, for that reason I showed you this the football picture, the football kick, the free kick. There also the similar thing is happening. When the ball is spinning, what happens, the air are different from the either side of the ball, and because of that, that ball, instead of moving in a straight line, it goes in the curved path. So Magnus force is responsible for the curved motion of the skyrmion. But let me tell you, we have to get rid of this Magnus force. This Magnus force is very interesting to sound, but for real application it is not useful, because if you have Magnus force, the skyrmion which you see now, they will go to your rightward side or the left side, it will hit the wall and it will be destroyed.
Okay, it's my question actually. So compared to GMR and PMR, how about 2D magnetism can boost the memory technology?
Oh, that's a very good question. That's a very good question. So I think 2D magnet is right now is a very hot field. Is since 2017 the first paper discovered, because 2D magnet, as no one know, as people who are here from the physics background, they know this. There is something called Wagner-Marmin model, and according to Wagner-Marmin model, it doesn't allow to stabilize a long-range ferromagnetic order, 2 spins order in a 2D ferromagnetic material, because of the thermal fluctuations. But interestingly, this 2D material has a strong anisotropy, and they can have a very long range ordering. Unlike people have been working on graphene, right? They wanted to make it magnetic, but it somehow did not work, or they are doing some atom, some doping. But now the recent discovery of the 2D magnet is really amazing, but the trouble is, 2D magnet, these materials are very unstable at ambient temperature. Their air unstable, and they are like and their magnetic ordering temperature is very weak. So we need a room temperature 2D magnet actually. So the 2D magnet, if one have, the 2D magnet can miniaturize, the device size, miniaturize the device, because 2D magnet is an atomically thin layer, atomically monolayer or bilayer. So you can actually make the Spintronics device even smaller device what we can imagine today. So I think 2D magnet has enormous possibility in the Spintronics device, but one has to really do a lot of work to develop a material at room temperature, and especially for their stability. Yep. Does it answer your question?
Still participants are asking so many questions. So
please ask them to email me. If they are not get enough time, please ask me to email maybe I can share my email address once again.
Yeah, exactly. So that will be good
So
idea.
this is the email address. This is the email address. Please note down and you can write to me. Any question?
So yeah, so we are sorry for the audience. So still a few more questions are there, but we have to go for next session. So we are very sorry. So if you have any questions, so please directly note down this email and ask to the speaker. Thank you. So thank you very much, Rana, for a very exciting and good talk. And personally and on behalf of our college and the entire team. So and thank you very much.
Thank you.
So next speaker, Dr. Swastika Banerjee. Ma'am, please welcome to this conference and it's open to session you.
Oh yeah, thank you. Yeah, can you hear me?
Yeah, we are getting your voice. You are getting.
Yeah, so let me share my screen. Yeah, so you can see my screen, right? Yeah, can you
Yes, ma'am, we are getting your screen.
Okay, thank you. So first of all, thank you, the organizers, for the privilege. It's really a great privilege for me to be in front of you. And when I heard first, it was from Rana via Sidhu and Satya. So I was not at all prepared because it was a busy schedule. But when I heard that it is an opportunity to talk to you, and especially the beginners in the field who are going to start the research, and I can be actually available to them through this. So I agreed without thinking whether I'm going to be prepared or not. So here, and I thought of making the presentation on theory and computation to achieve the high performance lithium superionic conductor. So in the beginning, I just would like to clarify that I'm a person who works on computation.
Sorry for disturbing you.
Yeah.
Your video is not on actually. So can you please switch on your video?
Oh, you want me to switch on the video? Yeah. Can you see now?
Yeah, now we are seeing.
Yeah.
Thank you.
So, okay. So I just would like to mention that I'm a person who worked on theory and computation since the beginning of my research career. And I mainly focused on energy storage. But apart from energy storage, I also worked on carrier transport, like how the electron or the charge carriers like hole getting transported through the materials. So with this background, I'm going to, sorry, once. Yeah. So I just would like to acknowledge my background and my places where I belong to. Especially, I'm going to present in front of you the study which I did in my postdoctoral period. And it is from Berkeley and San Diego. So I was in Lawrence Berkeley National Lab for 1.5 years. And then I moved to UC San Diego. And I have been there so far. At present also I'm there. And I have been involved in projects which are based on carrier transport and energy storage. So, and there are a lot of funding agencies, a lot of computational resources I must acknowledge before I start anything, including the CSIR, DST, Agene CSR, from where I did my PhD, CCMS, which was the source of computation during my PhD. So with this brief acknowledgement, I would like to start my presentation. So this is the research domain in brief for me. It's like electrochemical energy storage, especially the battery. So by battery, I have shown you the very simple schematic. It has 2 electrodes and the electrolyte medium in between. And this is a setup or device which allows the electronic flow through the outer circuit. At the same time, it needs the inner flow of the ions through the electrolyte medium. So battery or the cell is consisting of to simultaneous process of the carrier transport through outer circuit and ion transport through inner circuit. So it's a very simple statement to say about battery, but it's not that simple. There are a lot of chemistry, a lot of factors, device engineering to make the battery realizable in the market. So this is very brief introduction about the battery. And the next thing is I also studied the charge transport or dynamics. You can see several kind of optoelectronic devices or the transport devices which are having a component like graphene. You can imagine the 2D materials which are emerging recently, and depending on their carrier transport properties, we actually select and we think of the requirement for different transport devices. Like sometimes we need anisotropic behavior, sometimes we need very good electron conduction but not hole conduction. So depending on the transport properties, we choose the materials. So materials, and the next thing is which I was interested was the photochemical energy storage. Like how we can harness the solar power through storing it and then making it transportable through recyclable fuel. So this is also pretty interesting study, although I didn't have much scope to work on it so far, but I just began with and I enjoyed the work. So these are the main 3 research domains that I have been working on since my PhD days. So to be more focused for this presentation, I'm going to tell you about the analysis techniques, and then I'll go to especially the battery part, which I'm going to discuss. So the analysis techniques, as I told, I'm a computational person. So it has actually, in computational theory, you have a lot of assumption, lot of methods, lot of techniques, and it depends which is the problem you are going to tackle with. Since I introduced you to my problems, I'm going to tell you what are the techniques that I use. So the first thing is density functional theory. It's a very good, it's very promising, it's very well known, and everyone I think knows whether they use it or not. So what is it is basically the simple realization of the many body wave function in terms of one electron wave function, but I don't have much scope to discuss on the details of the method. But I would like to mention that from the density functional theory calculation, if we solve the Schrodinger equation, we can get the total energy, we can get forces, energy levels, corresponding wave functions, band structures. These are the ingredients which we get from the density functional theory calculations, and these are relevant for understanding the thermodynamic stability, relaxed geometry, or 0-point energy calculation, or the activation barrier, all kinds of static properties, or the 0 Kelvin features for the materials. However, we may need to go beyond the 0 Kelvin temperature. Then we need to consider molecular dynamics. And this is at finite temperature. We solve the Newtonian motion and we calculate sometimes the force field through ab initio study or some empirical way. So it depends on how accurately we want to do this simulation or what are the size of the system. So depending on the molecular dynamics strategy, we choose it depending on the necessity. And we can calculate the dynamics of the ions. We can see the diffusion barrier for finite temperature. And also we can see the sustainability of the electrode materials. So after the density functional theory and molecular dynamics, I was also interested in understanding some of the methods which are based on analytical and combined density functional theory and analytical methods, such as Boltzmann transport equation. And that's for the study of electron hole transport through periodic systems. I also worked on non-adiabatic molecular dynamics. This is pretty advanced method where we cannot apply the adiabatic methods like DFT. We need to think of the excited state dynamics in a sophisticated way. So that's the non-adiabatic molecular dynamics where we studied the hot carrier cooling processes or so. And there is another method which is basically it's like we need the grand canonical linear programming to make the phase diagram phase to understand the assembly and the properties through understanding the features which are existing. And it is the grand canonical linear programming is basically we need the energy data, or we need a library of materials, and we construct the phase diagram, and we extract the stability function depending on the relative position of the system of our interest. And there are a lot of excellent initiatives like Materials Project or OQMD. They are working on this data science, or how strategically utilize and how strategically make the data-driven discovery. So that's very interesting field, and for the near future to understand or design new materials. And in terms of materials engineering or material science, I feel we need to think of various possible ways of techniques. And with this introduction, I just would like to go to the topic that electrochemical energy storage, which I'm going to discuss with you today. So to begin with the battery, I think I don't need to introduce you the battery, because in everyday's life, we are always familiar with it. And you cannot imagine anything without battery. Like, you cannot think that headphones you are using and you are having the cord which is plugged in your home, you do not have a portable storage or battery with you. So at this current stage, or at the present scenario, we cannot think of the civilization without a portable storage through battery. So I think we don't need any more introduction that battery is a portable storage, and it is a smart, advanced, and the energy carrier. So to understand what is battery, basically what is lithium-ion battery, we are very much aware of the lithium-ion battery. So it's a very simple schematic of lithium-ion battery. And I mainly focused for this presentation to the beginners. So I didn't want to mention, I wanted to begin with the basics. So if you think of the battery, it has three components, like the positive host, which is meant as cathode, and then the electrolyte and the electrode, and the anode, the negative electrode. So the positive electrode hosts the lithium with high binding or the high chemical potential, and you have, the low chemical potential, and you have the storing of the same metal, or the settling metal like lithium in the anode with relatively smaller binding. So what you are going to do, basically thermodynamically, you are creating a potential difference of the same chemical species which is stored either of the sides of the electrode part. And depending on how different they are in terms of stabilization, you are going to get a voltage which is the overall voltage for the system. So to schematically represent the whole factor, it is the anode chemical potential in the left. In the right, it's the cathode electrochemical potential, and you must have to have the electrolyte medium, which is the transporter medium for the ions, that needs to be placed in such a way there won't be any electrochemical reduction or oxidation in principle when you are making a stable battery setup. So by this, what I meant is, if there is oxidation or reduction, it should happen at the electrode side, not in the electrolyte. But in reality, it doesn't happen. So in reality, what happens is, if we use lithium metal as the anode, we have many unwanted electrochemical reactions. At the same time, it also happens at the cathode side. There are electrochemical reactions and chemical reactions at the interfaces. So if we use the lithium metal anode, we can achieve the maximum possible capacity depending on how much energy you can store. But you have a lot of other difficulties, like the safety issue and the stability issue. So designing an insertion type anode other than the pure lithium metal anode could be a safer option to avoid such reactions at the interface and the dendrite formation. And also we can design some electrolyte rather than liquid electrolyte, which is actually reacting with the electrodes. We can make some inert electrolytes which are purely ion conductors, which are not participating in the electrochemical or chemical reactions, and making the stable setup. So this is a very ideal dream to make a battery that we can think of insertion type anode, which would be very safe and it will not be like lithium metal anode. Another case is like electrolyte, which will be solid state. It won't be liquid, but it will be very ideal. So, but we can imagine this kind of scenario, but how can we achieve this? This is actually next generation all solid state battery dream, that we have such high voltage cathode, we have lithium metal anode, and we have solid electrolyte. And we have very good cycle working on. But in reality, it's not true. It has a lot of difficulties, it has a lot of constraints, especially in terms of designing materials and controlling their properties. So I have shown here a dangerous picture that you see the battery, the car is getting fire. So we need to think of safety all the time. So when we think of any large scale, we can think if we have the solid state, it is very compact, it is highly energy dense because the stacking is very condensed, and we can use high voltage cathode, we can use lithium metal anode. But we need to think of the underlying mechanism or the several other factors. So to design ideal solid electrolyte, we need to consider few of the criteria, like the extremely high ionic conductivity, low electronic conductivity so that we can avoid short circuit. It should be stable in terms of phase, electrochemical or chemical. It should be mechanically compatible to make the device possible. So these are the requirements for the ideal solid electrolyte. However, how about the electrochemical energy storage, which we are the problems with the safety or the energy density, we are going to deal with these two strategies. And the first one is the insertion type anode, as I was mentioning. So insertion type anode is basically a van der Waals kind of materials, and we can intercalate the respective metals. Like for lithium ion battery is the lithium, for sodium or for potassium it's the respective elements. So we need to choose the layered system in that way that it will allow the intercalation chemistry, which will be not, it has a very tricky criteria, that how much energy can be stored depends how much ions you can store, and how fast battery can be charged, it depends how fast these elements can be transported through the material, because when you charge or discharge, there is a shuttling process of the ions from the cathode to anode. So you have two phenomena. One is the thermodynamics, that is the storing of the ions. Another is the dynamics. So it's the how fast it can be extracted or inserted into the electrode materials. So with these criteria, we need to think if we really want to store the system, to store the ions into the system, it should be a significant binding energy. But if it is too high, then we cannot extract it with low voltage. So for the anode, when we design the insertion type anode, we need to optimize the binding or the force, the materials, the elements we are going to store in between the layers. So that's the trick, that we need to choose the material not that binds elements, but also binds with an optimal amount of binding energy. So, and also how fast and how efficient it can store. So we actually were interested in my PhD days. I have been working for close to 5 years on different materials, and I'm showing you a few of the representative materials, which is the all are layered basically. So the first one is the boron sheet, and the second is the borocarbonitride. The third one is the graphene analogs. So it is, we have seen, and the lower panel is showing the phosphorine, which is the puckered structure. We find for the lightest 2D shade, which is the boron shade, it is actually very good in terms of the lithium metal storage. The second one is good for the sodium And the borocarbon, the phosphorine is very promising for magnesium ion. And we find this boron shade is actually metallic in nature. So it's very easy to be charged and discharged because the electron insertion and extraction is very fast. And the rate of lithium diffusion is also comparable to the graphene electrode. So it is actually promising for lithium ion storage or the insertion type anode for the lithium ion battery. When we look for the borocarbonitrides, we find that it is actually good in terms of diffusion for sodium, and it's even faster diffusion for sodium compared to lithium. And the charging, discharging, when we studied, we find it can store sufficient amount of sodium on this layered system. And we looked for the phosphorine kind of Packard structures, where we find that it acts as a covalent matrix and it stored the magnesium. Because magnesium is 2+ in charge, it's very hard to find a system which will store the magnesium with sufficiently low binding energy. Usually, whatever the elements or whatever the layered systems we find, those are having significantly high binding energy with the magnesium. So our design principle was such that to get a covalent matrix that will help reducing the magnesium adhesion to the system. And we also thought of stabilizing the activation barrier through the covalence so that the overall diffusion barrier will be reduced. So it will allow the fast diffusion for the magnesium through the system. So these are the 3 representative materials. Those are successfully proposed from the computation. And we found they are really promising for the lithium, sodium, and magnesium ion battery as the anode material. So with this initial results, I would like to go for the second choice that I mentioned, that solid electrolytes. That was very promising for me. I feel very interested actually, because it could solve many other troubles rather than just the liquid system. So it is. So what is solid electrolyte is a solid crystal, but it is the conductor for ions similar as the liquid materials. So it seems very crazy, right? So it is a solid conductor, it's a solid system. So we know that solids are static, they are not mobile, but how can a solid may conduct a particular ion? So that is the design, that some of the solid structures are such that they have the framework which is very strong. They are like crystal or they are like glass, and they have a certain ion like the sodium or lithium or magnesium, which are the mobile ions. Those are actually mobile, but the framework remains stable. So it's an excellent concept that we can replace the liquid electrolyte, which is the conductor for the ions, with the inorganic materials, which are the solid crystals. So with this strategy, we can achieve improved energy density, higher voltage, higher compactness, high lithium transference number, because you have no scope to have the transport for the anionic species. You are just having the cationic species. It is also safe and portable, and it's linked for the lithium sulfur or lithium ion batteries, because we cannot use the liquid electrolytes for those upcoming technology. There are a lot of difficulties like polysulfide dissolution, or there are chemical reactions or redox processes for the air batteries. So we can avoid those difficulties through designing the solid materials rather than the conventional liquids. So with the basic difference between a solid conductor and a liquid conductor, as I mentioned, it's really hard to find the potential energy surface which will be as shallow as the liquid. Because in solid, the conduction happens through discrete potential energy surface, and it is a very corrugated potential energy surface. The metal ions or the respective ions which is passing through needs to actually pass through a very high activation barrier. But for the liquid, it's a coherent process, and it's actually cooperative. Sometimes it gets a cooperative influence by the solvents. So it's very, the mechanism of the solid and the liquid conductions are very different. And this is the reference. You can find the details about the mechanism and other stuffs. So the main obstacle with the solid electrolyte is the conductivity, because it's very hard to find the low activation barrier with the solid. And it's very hard to get a low interfacial charge transfer kinetics between two solids when you combine the solid electrolyte with the electrodes. And fundamentally, we do not have any guiding principle that we can design a solid electrolyte. So these are main three obstacles to get a new material which will be a potential solid electrolytes. So if we look back the literature, people have started working on the solid state ionics since 40 years or so, even back, I think even back in 60, they started the solid state ionics. But the concept of solid electrolytes and applicability of it into the device for the electrochemical energy storage came very recently, and it is still going on, and there is no successful marketized thing with the solid electrolytes so far, which will compete with the liquid electrolyte. So if we look at the literature survey, we find the Li10 G P2S12 is one sulfide-based conductor, and Li7P3S11, this is also one glass materials, which is also based on thiophosphate framework. They are actually very promising in terms of the lithium ion conductivity. And if you see the scale for the conduction, these are actually in the order of 10 or more than 10 millisiemens per centimeter. So these are really competitive to the conventional liquid electrolyte, and surprisingly, we are actually now we are now crossing the limit that we are beyond the liquid. So with solid, we can achieve the conductivity. However, there are several other issues like the stability and other stuffs. So if we think of the solid electrolytes like sulfides or several oxides, oxynitrides, in terms of their performance, we find sulfides are quite promising in terms of the self voltage or power density or the cycle life. However, there are promising oxides electrolytes or the polymer electrolytes, which are still, and they still need some more study or to be understood well, or to be understood in terms of their practical applicability. So why sulfides is their softness, their applicability to make the device setup. And it is the famous LGPS framework, as I have told you, the conductivity is competitive to the liquid electrolyte. And this is the framework which is actually interesting, especially for the beginners. I would like to introduce you to the framework, and you will be really excited to see that this is a solid framework. This is a crystal kind of framework. You see, the arrangement is such that the lithium ions, which are the green color, green and the white, that says the partial occupancy, these are basically free to be mobile. So this framework is such an excellent framework. You have a static crystal framework, but you have the sublattice, which is mobile. So this kind of systems, if we want to realize, we have two strategies. We can actually computationally design the framework and experimentally study it. And we can, in the next step, we can make the successful device with lot of considerations or lot of minute details about the reactivity, their stabilization at the interface, the resistance at the interface, all those kind of understanding on the device setup. So here I have shown a computational result from the ab initio molecular dynamics, which successfully predicts that these are the framework which can give you very good diffusivity for the lithium ions. And the activation barrier estimated from theory and the experiment, they matches pretty well. So that says the excellent prediction capacity for density functional theory or the ab initio molecular dynamics to design the materials. And in fact, these materials has been also realized in the experiment. So we have a very good agreement with the computation and experiment in this material science background. So when we look at the system, the basic thing which we need to know is why it's good conductor, what are the design principles, so that we are not only limited to this framework, we can design some more new. So it is the anatomy of the superionic conductors that I just want to share with you here. For the LGPS, we are basically showing you the framework for the anions, like the sulfur anions, which are forming a BCC kind of lattice, and the lithiums are moving from one tetrahedra to the another tetrahedra. So it is via a phase center, via the triangular phase. So that kind of arrangement for the anionic species give rise to very fast conduction for the lithium metal, for the lithium ion in the framework. So with this, when we see this principle, we can actually correlate with lot of other species, actually, lot of other materials, lot of other systems, that this kind of BCC sublattice for the anions are really a good designing principle to make another superionic conductors. So this is, I think, it's a power of computation, it's a power of analysis, that you can design new materials for the future. So with this, if we so far we have discussed about the diffusion properties, but there is another thing which is very important, is the electrochemical stability. So what is the electrochemical stability? Is when we combine the electrolyte with the electrodes, we are basically having two drastic potential situation, I mean electrochemical potential at the two different electrode sides. So when you have the anode and the cathode, the lithium ions and the lithium can act as the anode can act as the lithium source, and the cathode can act as the lithium sink. So you can have the lithium ion redistribution at the electrode electrolyte interface, and also depending on the voltage applied, you will see the lithium can be removed or inserted from the conductor to the electrode, and that requires the oxidation reduction, so which is not at all intended to make a stable device setup. So what we need to understand the stable electrochemical window, which will not allow such kind of insertion or extraction of the elements like lithium ion here for sake. So we just want to define that quantity, that this is the electrochemical stability window where we can operate without any kind of reaction, with any kind of exchange of lithium at the interface. So the how to calculate such electrochemical stability window? So it's basically, we can construct the thermodynamic phase diagram, thermodynamic equilibrium under different electrochemical potential for lithium, and we can study what are the stable products at the interface. So as for example, I have shown here the LiCO2, LPS, and lithium. This kind of device, this kind of setup, if we consider, we have different products at the electrolyte interface at the limit beyond the stability window. So it says basically we have a limited potential to operate for such electrolytes. As for example, for the LGPS I have shown here, if we construct the similar way the phase diagram at different electrochemical potential for lithium, we find that the potential window where the LGP is stable is indeed very narrow. and it is actually dictated by the stable other possible products which are existing and which can be potentially formed depending on the thermodynamic criteria, that you cannot go beyond the limit. So it restricts you for the limit of operation for the solid electrolytes. So we can have an idea about the electrochemical stability window from constructing the grand potential diagram. And the phase evolution, we can definitely consider multiple actually chemical species, and we can construct the complex phase diagram, and we can find what are the stable situation, what are the products forming. So this is the very smart approach to define the stability window. And this is actually is done by the excellent initiative from Materials Project. You can actually email me or talk to me. Materials Project is very efficient from the framework, and it gives you a lot of freedom to analyze the materials properties or to understand several kind of aspects like the phase diagram, or to access the library of materials. You do not need to calculate anymore which are existing in the database. So it's a very good initiative for the whole material science community to understand, to design new materials. So it's another application. You can see that not only single electrolyte, you can actually apply for multiple systems, and you can screen which one is suitable for which electrochemical window. Like in this plot I have shown here, the Li2S is actually excellent in terms of the anodic stability. So if we reduce the possibility of the metal reduction, then it is stable at the lithium metal anode side. And we find comparison with the all other solid electrolytes, Li2S is good in terms of the anodic stability, although it is not good in terms of the conductivity. So you have a trade-off between the stability, conductivity, several factors. So we just need to consider all these features, and these are the smart screening approach to design the final excellent materials for the device. So if we look at the other thing, like the anodic side, we find the oxide-based systems are really good in terms of the anodic stabilization in comparison with the sulfides. So it also depends on how strong hybridization is and how the voltage stability. Actually, there are a lot of chemistry I can discuss with you in details, where I feel the time is very limited. But for this stability window and how to understand the what dictates the oxidation limit or the reduction limit is very basic. It's like you can think in terms of molecular orbital theory, that how the hybridization or how the exchange happens and how easy the redox process, it depends on the chemistry, or it depends purely on the bonding pattern for the system. So with this, so far we discussed about the electrochemical stability part, and before we discussed about the diffusivity. Now another thing is the moisture sensitivity, because when we think of any materials to be practical, we need to understand the ambient condition stability. So the moisture sensitivity for solid electrolytes like sulfurs, we just wanted to know for a representative material like Li7P3S11, we constructed the 4-way diagram, and we find there is a certain limit of the voltage window that we find the products are no more solid in phase. So those are basically either liquid or gaseous. So if they form in terms of the thermodynamics, it is supported by the thermodynamics. So if they form, you are basically having an unstable situation for the electrolyte. So the 4-way diagram is a smart approach to understand the moisture sensitivity of the electrolyte. And here I have shown the representative one, but it's not limited just for one. You can also think of the similar picture, similar scenario to screen whether it is really good or not in terms of their ambient real application. So with this, we understood the stability aspects, diffusivity aspects. Now, if we compare the oxide versus sulfide, we find there is a distinct difference between the oxides and the sulfides. So oxides are very good in terms of high chemical stability, mechanical strength, and high electrochemical oxidation voltage, as I have shown you from the oxidation potential for the phosphate for the oxides. So in terms of the sulfide, we find they are highly conducting, even much more higher in terms of conductivity than the oxides. They are good mechanical strength, they're low grade boundary resistance, but the disadvantage with the sulfides is the low oxidation stability, the sensitivity to the moisture, and these are not really compatible with the cathode materials. And also there is also limit for the anodic voltage. So we have a bunch of advantages and disadvantages for either of the classes. So what I see is the oxide versus sulfide. There is a stability versus conductivity. These are the two prime factors actually comes into the picture. So if we think of Li2S, P2S5 glass, and there was an interesting study that if you add some Li2O in it, so it's basically a mixed sulfur oxygen framework, and that's a rational designing. And it says that you can actually increase the stability after putting Li2O, and overall capacity is not that bad. However, the conductivity is very poor. So with this initial information that sulfides are bad in terms of stability, good in terms of conductivity, oxides are good in terms of stability but bad in terms of conductivity. So we are basically wondering what to do to make a new class of solid electrolytes. So again, I looked back certain literatures and found that if we incorporate the oxygen in the sulfur framework to a certain extent, there is actually a specific chemical stoichiometry that allows the better stabilization, and the conductivity also increases. So that makes me very excited. So there could be some possibilities to design the material where we are not losing conductivity but gaining stability, to make it more reliable or practically applicable. So that's the experimental findings from LGPS, that the moisture stability and better cycle life for this particular composition where you have some oxygen in the LGPS framework. However, we still do not know whether there is which is the optimum oxygen concentration to maximize the stability, and how does this oxygen content affect the ionic conduction. So we just wanted to know, we wanted to again question on what does oxygen substitution do here, and does it preserve the conductivity? And so far, if it is if it does that, then what should be the optimum composition to do that? So we wanted to look for some new class, which is the oxysulfide class of materials, with this this desire that stable framework with preserved conductivity. And again, I'm just showing the LGPS framework because I worked on this LGPS framework, and this is the summary so far which I have mentioned. So the key limitations are again moisture sensitivity, interfacial instability, and the electrochemical stability window. So what we did is we mixed the oxygen into the framework of the LGPS, and we find that if we keep on increasing the oxygen concentration, at certain intermediate concentration, we have the minimum energy or the stabilization. So this particular composition, which is the most stable, has the phosphate in it and GeS4 tetrahedra as the sulfide counterpart. So this is a mixed oxygen sulfur framework, which is very stable, even more stable than the parent compounds like LGPS and LGPO. And we can actually think that it could be a potential candidate in terms of synthesizability, because in terms of thermodynamic stability, they are promising. Now, if we, so this is the zoomed in figure or the picture for the proposed material, the middle one, which is the sorry, these are the two terminals, like a GeO4 PO4 and GeS4 PS4. However, you have now the sulfur oxygen mixed framework where you have GeS4 and PO4. So if we compare the stability and look at the phase diagram, again the materials project comes into the picture. You can do the similar studies using the data analysis. So you see the phase diagram, the LGPS stands in a very safe position where it's a stable compound. The LGPSO, sorry, not LGPS. So LGPSO is a stable composition here. So increased thermodynamic feasibility it is observed, and the phase decomposition, if you look at the right hand curve, it is actually getting lower and lower. That says this is getting destabilized in some terms of the decomposition. However, the moisture stability increases. So with this initial study on the stability in terms of the phase, we wanted to look for the electrochemical stability window. And we find that for LGPS, we have the stability window here in the extreme left corner. The LGPSO or the another components, like instead of germanium, if we put the silicon or tin, we have the modulation of the electrochemical stability window. So you can clearly see the stability window is much more wider in comparison with the LGPS when we have oxygen in the framework. So this is a superior compound or superior design for the next solid electrolytes with respect to the state-of-the-art LGPS. So if we see the stability window, you can see the products which forms the below or above the oxidation or reduction limit, and you see the stability window is actually much more enhanced, and you can basically tune it through such strategy. And you can, if you change from silicon to germanium or tin, or sorry, germanium to silicon or tin, you can again have the freedom to push the oxidation limit higher or the reduction limit to the lower, or to tune that. So this is a smart approach again, through designing the material to make them more applicable depending on which are the electrode in use, because the usability of the electrolyte depends what is the potential electrode chemical potential that the electrode operates. So we need to choose the electrolyte in a smarter way after keeping in mind that what are the potential electrodes. So this is, we find the highest cathodic limit can be obtained by tin, and enhanced anodic limit can be obtained by silicon. So this, I again show you the lithium diffusion properties for the LGPSO. So far, what we were expecting that we'll design something which will be more stable, but it will not sacrifice the diffusion. So we really found that this LMPSO. Can you hear me?
Yes, madam.
Yeah, I just found the host has muted you. Yeah. Am I audible now?
Yes, madam.
Yeah, so, yes.
Okay.
Yes, madam, you are audible.
Okay, sure.
A few more questions. So I will read it. The first one is, why TiS2 has higher discharge voltage than TiO2? Although both cases same Ti redox
Sorry, it's not at all audible. Can you hear me? Hello.
Can I read out the question?
Yeah, I can hear you now.
Why TiS2 has higher discharge voltage than TiO2, although both
Your voice is getting broken actually. Is it only me that I cannot hear, or everyone can hear you clearly? I don't know which part is problematic. Maybe
It's not audible to me as well.
Madam, you are audible, but
I will read it one more time.
yeah. Yeah, now I can
Why
hear you.
TiS2 has higher why TiS2 has higher discharge voltage than TiO2, although both cases same Ti redox participate.
Okay, actually any redox process, it's not only depending on the element which is the metal, it depends on how bonding exists. Like you have the TiS2 bonding or TiS2 framework. As I have shown the hybridization concept, when we show the oxidized products like the phosphates are having very good electrochemical stability window at the oxidation limit. So it depends on the hybridization, on the bonding, the redox process, at which potential the redox process will start. So if you compare the bonding of the TiS2 and the TiO2, so although it is the titanium, which is the metal, it's not the same bonding pattern as the sulfide or the oxides. So you will always have the modulation, and it depends. It's very general. It's not only for TiO2 or TiO2. You can find for any other compounds too. You will have a minute modulation, but it depends what is the extent of modulation. That depends on the strength of the hybridization.
Next question. Is there any way to create pure lithium cell?
Pure lithium cell. Yeah, lithium symmetric. Actually,
Yes.
the lithium symmetric cell, it's a hypothetical concept that you can basically make a potential gradient between the two parts, between the you can keep the same lithium at two different chemical potential. So in principle, you can make battery if you generate the voltage difference. So you can make the symmetric battery. You can make the actually there could be a single material battery setup, like LGPS can act as the electrode and the so you can make a cell which is made up of just one material. But it is the concept that you have to put them at two different potentials.
Yeah. Now, really, it's a very exciting talk, and thanks for all the speakers. Now, I request Dr. Ramanna for vote of thanks. Sir, nim's audio unmute ಮಾಡ್ರಿ.
A very good evening to all present over here. It gives me an immense pleasure to deliver the vote of thanks for this event to all dignitaries assembled here. Firstly, I would like to thank our distinguished speaker, Dr. Satyanarayan Gwin, postdoctoral fellow, Department of Solid State Chemistry, Max Planck Institute for Chemical Physics of Solids, Dresden, Germany, for making excellent presentations and making this seminar interesting and meaningful. Thank you, sir. I must mention our deep sense of gratitude for Dr. Rana Saha, postdoctoral fellow, Max Planck Institute of Microstructure Physics, Weinberg, Halle, Germany, for his wonderful explanation about magnetic fields in future data storage devices. Thank you, sir. I also wish to express my gratitude to Dr. Swastika Banerjee, postdoctoral fellow, Nano Engineering Department, University of California, San Diego, USA, for excellent talk on the topic of theory and computation to achieve high performance lithium superionic conductor. Thank you, madam. I would like to express our gratitude our principal, Professor U.R. Rajput Singh, for his support and encourage for conducting virtual conference. Thank you, sir. I'm happy to express vote of thanks our HOD, convener, organizing secretaries, and staff members of Physics Department, KLE's BK College, Chikodi, who have made this conference a grand success. And I would like to thank faculty members of Chemistry Department, KLE's BK College, Chikodi, for their technical support. And I would like to thank all the participants for making this conference a great success. And finally, I thank you one and all. Thank you.
Okay.
Thank you very much, sir. Thank you very much, Ramana sir. And thank you, Swastika and Rana and Satya for wonderful talk. And really, it will be helpful for our students also. And if any questions is there, directly we will transfer to you people. Huh? Okay. Thank you once again. And now we can do the meeting and participate. We have already shared the feedback, shared this feedback link. Participants, please fill the feedback link and get your certificate.
Thank you. Thank you very much.
Thank you very much. Thank you.
Thank you.
Bye.
Bye.
Okay, bye.
Bye.
Hello.
Yes.
Sir, please share
Hello.
the feedback form. Feedback link
Yes.
form.
Okay.
Hello.
Good evening, sir.
Sir. Hello.
Hello, hello, sir. Hello.
Madam, everybody asking a feedback link form once again in the chat box, please.
Sir, actually, host is on mute, I think.
No, madam. We are waiting for that one.
Hello.
Share once again, please. Many lecturers are asking again and again.
Hello.
Sir, we are in queue now.
No, actually, feedback form is not shared.
No, sir, there is no feedback form.
Yeah, actually, feedback form is not shared by the organizer.
How to fill the link in a group or chat box, sir?
Okay. Telegram.
It is requested the organizers to share the feedback form.
Sir. Actually, feedback form is not shared.
Okay, thank you.
Hello.